So I forgot to mention one small thing. That is, when you are multiplying, let's say, this row by minus 6 by 18, you have to multiply everything here by minus 6 by 18 and also this by minus 6 by 18, the right hand side. Otherwise, they don't remain, the problem doesn't remain equivalent to the original problem. And when you subtract, then you have to subtract this from this as well. As a result, these numbers also keep on changing with every elimination. Now, in a finite element context, this has a kind of physical explanation which we can explain through a problem like this. Imagine that we have a finite element structure, in this case a beam which is simply supported, and there are only 4 nodes and with 1 degree of freedom per node, and these degrees of freedom are u1, u2, u3, u4, and there's a concentrated load r2 applied at node 2. These are the node numbers. There's a concentrated force of magnitude 1 or minus 1 applied at node 2. No other node has a applied force. So now suppose again that the stiffness matrix, the global stiffness matrix after assembly is this, and this is your external force vector, and you are going to solve for u1, u2, u3, u4. Now to do that, what you are going to do is you are going to multiply the first one by minus 4 by 5 and this side also by minus 4 by 5. That will give you 0, and then you will subtract it from the next row. So when you do that, then in the next step you will multiply it by 1 by 5, subtract it from this row, and then you will multiply it by 0 by 5, subtract it from this row. In the process, all these 3 elements of the matrix will become equal to 0. You will then continue doing that with this and then doing that with this. In the end, you will get an upper triangular matrix. In the whole process, your right hand side will also keep on changing, and when you do the first row, it's the first elimination step. What it does is it turns these 3 into 0 and therefore eliminates u1 from your system of equations, and it also modifies the right hand side. In this case, obviously the right hand side doesn't get modified because this is 0, but that's only by chance. In general, the right hand side will get modified. So at the end of the first elimination, what you have is a matrix which is 3 cross 3 rather than 4 cross 4, because the first row and the first column, the first degree of freedom u1 has been eliminated, and now the problem that you have is you have got rid of 1 degree of freedom, and this is the equivalent problem that you have. Equivalent in the sense that the solutions to u2, u3, u4 are still the same as that of the original problem, and this is the resultant problem which has the same solution as the original problem with 1 degree of freedom released or eliminated. When you do the next step, which is like you now have to eliminate these two, so what you will do is you will multiply this by minus 16 by 5 by 14 by 5. The left side as well as the right side, you will also multiply this by 16 by 5 divided by 14 by 5. Subtract it from the second. You will now eliminate u2. You will get a 2 cross 2 equation. 2 degrees of freedom are left, and now your forces are 8 by 7 and minus 5 by 14, which you have applied at nodes 3 and nodes 4. So this is the equivalent system. This is the equivalent system after the second elimination. The equivalent system after the third elimination is this, where you have so this is equivalent to the original system that we started with, and now we can solve for u4 directly from this. So from a physical standpoint, we can argue that in an actual finite element problem, we should never encounter a 0 at the diagonal. While we are doing this elimination, we should not encounter a 0 here, because because the structure is always stable. For a stable structure, the stiffness matrix has to be non-singular, and for a non-singular matrix, we should not be encountering a zero in the diagonal ever. But that is if the structure is stable. This is true in finite element simulations of elastic systems. You generally do not encounter uh, uh, zero along the diagonal, unless if you do so, if your Gauss elimination fails because you are encountering a zero in the diagonal, it would probably mean that your structure is not stable. It's not a static problem, and you have not fixed your rigid body modes in the problem properly. So that can lead to a zero. Otherwise, uh, problems in linear elasticity are supposed to give you matrices that will never turn up zero along one of the diagonals. However, pivoting will still be necessary because of reasons that we will discuss after this. So after this, we will look at the Gauss elimination process a little more formally and try to figure out the number of mathematical operations that are needed for one set of matrix equations.